December 16, 1944. 0630 hours, Mountschau, Germany. Hetman Klaus Riecha of the 12th SS Panzer Division sat hunched over a frost-lined notebook, his pencil moving in urgent strokes. The entry he recorded that morning would later be regarded as one of the most harrowing first-hand accounts in German combat records. He described a new American weapon that seemed to defy all known military strategy. German troops were being annihilated in their foxholes by artillery rounds that detonated above them in midair. No traditional defenses could shield them. The sky itself had become the executioner. Earlier that morning, Riecha had observed the complete destruction of a battalion attempting to traverse open terrain near Henn. Direct hits were rare. Conventional artillery with timed fuses required meticulous calculation and were far less deadly. What he witnessed instead was unprecedented. Shells that detonated automatically above soldiers' heads, raining lethal shrapnel over the ground in patterns that made trenches and dugouts almost useless. Within 3 minutes, 702 German soldiers had been killed. The few men who managed to retreat were so traumatized that they could utter only a single phrase, "Die Luft tot," the air kills. At the time, Riecha could not have known that he had seen the first operational use of the Americans' most tightly guarded weapon in the European theater, the proximity fuse. This device, essentially a tiny radar system embedded in an artillery shell, was the first example of a smart munition. Its impact on the battlefield was transformative. It multiplied the lethality of artillery by an order of magnitude, saving tens of thousands of Allied lives and changing the character of modern warfare. Conventional shells required roughly 500 rounds to destroy a single enemy aircraft. Proximity-fused shells achieved the same result with only 155. In infantry engagements, typical artillery would neutralize entrenched soldiers only about 5% of the time, while proximity fuses achieved casualty rates of roughly 70%. When countering the V-1 flying bombs over London, these shells destroyed nearly 80% of incoming missiles within the first month of deployment. The story of the proximity fuse did not originate in the United States, however. Its genesis traced back to one of Britain's darkest hours. On October 30, 1939, amid the looming threat of defeat and the first harsh winter of the war, a young British scientist named W. Butt submitted a proposal for a revolutionary concept. This innovation, born from necessity, would ultimately lay the groundwork for a new era in military technology and redefine the way artillery was employed on the battlefield. During their tenure at the Air Defense Research Center, scientists Edward Shea and Amherst Thompson began exploring a concept that, at first glance, sounded almost like a plot from science fiction: an artillery shell capable of autonomous decision-making. This idea did not emerge from imagination alone. It was born out of the stark realities of wartime calculations. In the First World War, anti-aircraft gunners had to expend an astonishing 8,500 rounds on average to down a single enemy plane. By the onset of World War II in 1939, with aircraft traveling faster and at higher altitudes, the efficiency of traditional anti-aircraft fire had deteriorated even further. The survival of Britain against aerial assault relied on finding a radical improvement in these odds. The solution envisioned was a fuse that could sense an approaching aircraft via radio waves and detonate at precisely the optimal distance. Yet the technological hurdles were immense. Any device had to endure the extreme forces of being fired from a gun, experiencing over 20,000 times the force of gravity, rotating at speeds of 30,000 revolutions per minute, surviving temperatures ranging from -50 degrees Fahrenheit to over 100 degrees Fahrenheit, and simultaneously maintaining the sensitivity to detect aircraft mere tens of feet away. By June 20, 1940, British engineers had built experimental models and conducted trials using unspun projectiles, resembling small rockets, aimed at balloon targets. These experiments demonstrated that the concept was technically feasible, but underscored the sheer scale of the engineering challenge. No electronic component of the era could survive the stresses imposed by artillery launch. The breakthrough would eventually arrive from across the Atlantic, brought by one of the most critical scientific exchanges in modern history. On September 6, 1940, the Canadian Pacific liner Duchess of Richmond docked in Halifax, Nova Scotia, carrying cargo of extraordinary strategic importance. Among its precious contents was a black metal case containing Britain's most sensitive military technologies, transported by Sir Henry Tizard. This event, later known as the Tizard Mission, marked an unprecedented decision. A nation on the brink of survival sharing its most guarded secrets with a country not yet engaged in the war. The British delegation reached Washington, D.C. on September 12th, taking up residence at the Wardman Park Hotel. Over the following week, they disclosed an array of advanced technologies: early radar systems, jet propulsion concepts, explosives innovations, and chemical weapons research. However, on September 19th, during a session in a conference room overlooking Connecticut Avenue, a key demonstration took place. British physicist Dr. John Cockcroft presented their progress on the proximity fuse to a young American physicist, Dr. Merle A. Tuve, who had been specifically requested for this briefing. Tuve, 39, raised in rural South Dakota, had spent his youth experimenting with radios alongside his friend Ernest Lawrence, who would later earn a Nobel Prize. Only a month prior, in August 1940, Vannevar Bush had assigned Tuve to lead a newly formed, highly secretive branch of the National Defense Research Committee, Section T, dedicated solely to developing proximity fuses. The selection of Tuve for this role was far from coincidental. That summer, he had listened to harrowing radio broadcasts of the London Blitz with his wife, Winnie. Reports described entire neighborhoods obliterated in minutes and children being rescued from rubble. The inadequacy of Britain's anti-aircraft defenses weighed heavily on him. Moved by the devastation and determined to make a difference, Tuve resolved to find a solution capable of countering the relentless bomber raids. In the conference room in Washington, a pivotal moment was unfolding. Cockcroft presented Tuve with a rare and extraordinary opportunity, a concept developed in Britain that could change the course of warfare. Although brilliant, it remained purely theoretical. No one had yet resolved the critical technical challenge: how to design vacuum tubes and electronic circuits capable of surviving the extreme forces of being launched from a gun barrel. Cockcroft acknowledged the limitations of British industry. They simply lacked the scale, resources, and manufacturing capability to undertake the extensive development program necessary. Only the United States, with its vast industrial infrastructure and geographically secure location, had the capacity to bring this vision to life. Tuve left that meeting charged with a mission that would dominate the next 5 years of his career and mobilize the entire American electronics sector. The obstacles seemed insurmountable. Achieving success would demand technological innovations that did not yet exist, manufacturing methods never before attempted, and production at an unprecedented scale. By December 1940, the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, D.C., had established a central hub for America's most classified weapons initiative. A mansion at 5241 Broad Branch Road had been converted into an operational command center. Tuve assembled a team of extraordinary scientists and engineers, each with specialized expertise that would prove essential. Among them were Richard B. Roberts, a nuclear physicist with experience alongside Niels Bohr; Henry H. Porter, a specialist in acoustics; Robert B. Broad, who had studied cosmic rays; and Lawrence Hofstad, a nuclear physics expert. Lloyd Berkner, known for his pioneering work in ionospheric research, also joined the team. A young physicist, just 26 years old, named James Van Allen, who would later gain worldwide recognition for discovering Earth's radiation belts, was entrusted with one of the most formidable tasks of the project, though his wartime contributions would remain classified for decades. The technical challenge was unprecedented. The proximity fuse had to function as a fully integrated radar system, combining a transmitter, receiver, amplifier, and detonator into a space no larger than a standard coffee can. It had to emit radio waves, detect their reflection from nearby targets, process the signal with precision, and trigger detonation, all while withstanding forces that would obliterate any conventional electronic device. Van Allen's assignment focused on the most critical component, vacuum tubes capable of surviving the extreme acceleration of being fired from artillery. Conventional vacuum tubes, with their delicate glass envelopes and fine filaments, could not endure forces exceeding 100 times the force of gravity, whereas the fuse required resilience at accelerations exceeding 200 times gravity. For 6 months, Van Allen collaborated with Raytheon, a Massachusetts company specializing in hearing aids, to develop compact, ruggedized tubes. Departing from traditional designs where filaments were suspended on fragile wires, the team engineered rigid, reinforced structures using techniques adapted from hearing aid technology. The breakthrough occurred in January 1942, when Van Allen devised a mechanical system inspired by the concept of a mousetrap spring. This mechanism shielded the tube's filaments during the intense launch forces and released them for normal operation once the device was in flight. The invention represented one of the most significant electronic advances of the war, though its patent remained classified until 1947. Meanwhile, Lloyd Berkner made a critical contribution in December 1940 by developing a circuit architecture that separated the transmitter and receiver functions. This design greatly enhanced the operational range and reliability of the proximity fuse, surpassing the earlier British autodyne concept. His innovation ensured that the fuse could detect targets at longer distances with greater accuracy, a necessity for its effective deployment in combat. Together, these breakthroughs in materials, circuit design, and miniaturization laid the foundation for a technological leap that would revolutionize munitions and alter the future of warfare. The work demanded not only scientific ingenuity, but also industrial coordination on a scale previously unseen, setting a precedent for the collaboration between research and mass production that would define the American war effort. By March of 1942, the research project had outgrown the facilities at Carnegie. In response, Johns Hopkins University established the Applied Physics Laboratory, APL, inside an old vacant Chevrolet showroom located at 8621 Georgia Avenue in Silver Spring, Maryland. When the first team of scientists arrived, the building still carried the lingering scent of motor oil and rubber from its previous life as a car dealership. Within a matter of weeks, however, it had been transformed into one of the most sophisticated electronics laboratories anywhere in the world. Merle Tuve was appointed as the laboratory's inaugural director. He quickly established a working environment and ethos that would influence the development of American weaponry for many decades. The walls were plastered with blunt, uncompromising slogans meant to guide and motivate the researchers. One sign instructed, "Do not waste money in this lab, save time instead." Another reminded the team of the gravity of their mission. "Our moral responsibility extends all the way to the battlefield. A failure there is our failure." The technology they managed to produce remains astonishing even by contemporary standards. The proximity fuse, in particular, functioned as a continuous wave radar system, transmitting in the range of 180 to 220 megahertz, frequencies that in 1940 were considered cutting edge. The projectile's metal casing itself acted as the primary transmitting antenna, energized by a small conical antenna embedded in the nose. The system used an autodyne design, in which a single oscillator tube simultaneously served as transmitter and receiver, a compact elegance dictated by severe spatial limitations. All of this advanced electronics had to fit inside a cylindrical space scarcely 5 inches long and 2 inches in diameter. Within that tiny envelope were 4 miniaturized vacuum tubes, roughly 130 individual electronic components, a wet cell battery, safety interlocks, and the detonator mechanism. The oscillator tube produced a base signal at 70 MHz, which generated harmonics spanning 180 to 220 MHz. When these radio waves reflected off approaching targets, the interaction created interference patterns that modified the oscillator's electrical load, producing beat frequencies between 200 and 800 Hz. These signals were subsequently amplified through a two-stage system, filtered to detect only the frequencies corresponding to nearby targets, and finally used to trigger a thyrotron gas-filled tube that detonated the shell. A critical challenge was the power supply. Conventional batteries were incapable of withstanding the extreme G-forces of artillery firing or delivering sufficient energy within the limited internal space. National Carbon Company devised an innovative solution, a reserve battery using liquid electrolyte sealed in a fragile glass ampule. The firing shock shattered the ampule, and centrifugal force from the spinning shell forced the electrolyte into stacked carbon and zinc plates, activating the battery mid-flight. This design allowed the battery to remain dormant indefinitely before use, while guaranteeing full power at the exact moment it was required. Multiple safety systems were built into the shell to prevent premature detonation. Centrifugal switches kept the fuse inactive until the shell reached the necessary rotational speed. A 1/2 to 7/10 of a second arming delay after firing ensured the shell could not explode near friendly forces. The sensitivity of the fuse gradually increased during flight, reaching its peak effectiveness precisely at typical combat ranges. The fuse's first operational test in combat occurred on January 5, 1943, in the Southwest Pacific near Guadalcanal. At 0800 hours, radar aboard the USS Helena detected an incoming flight of Japanese dive bombers, 4 Aichi D-3A Val planes descending from 12,000 feet. Lieutenant Russell Kern Red Cochran, in command of the aft 5-inch battery, had only recently been briefed on the new ammunition. In the ship's magazine, gunners loaded shells marked with distinctive green bands, signaling their proximity fuse capability. As the rangefinder reported the aircraft closing to 8,000 yards, Cochran observed the planes through binoculars. Unlike conventional rounds, which required direct hits to damage fast-moving aircraft, a near impossible task, these shells only needed to come within approximately 70 feet of a target. Orders were given to commence firing. The first salvo arced through the morning sky, but the planes remained unaffected, still too distant. A second salvo followed just 15 seconds later. At roughly 5,000 yards and 11,000 feet altitude, one shell passed close enough, about 60 feet, to the lead bomber. The detonation was unlike anything Cochran had seen before. Instead of exploding on impact or continuing past the target, the shell detonated mid-air, sending fragments outward in a near-perfect sphere. The Val's wing was sheared off instantly. Its engine, perforated by hundreds of metal fragments, erupted into flames. The aircraft did not explode in a dramatic fireball. Rather, it simply ceased to fly, collapsing from a controlled dive bomber into a tumbling, burning mass of aluminum and steel. The call came through the spotting station, "Splash 1." Immediately, the remaining Japanese Vals halted their assault, but Helena's anti-aircraft batteries remained locked on target. Within moments, 3 more salvos were fired, sending 12 additional shells equipped with proximity fuses toward the enemy aircraft. One Val disintegrated as a shell exploded approximately 40 feet beneath its fuselage, propelling shrapnel upward that tore into fuel tanks and killed the pilot instantaneously. In the ship's radio compartment, the engagement report was already being drafted. Enemy planes encountered specialized ammunition, 2 confirmed destroyed, and the performance of the new rounds far exceeded expectations. Yet the report failed to convey the psychological transformation experienced by Helena's crew. Gunner's Mate First Class Anthony Pui later reflected on the moment. "We had spent months firing countless rounds with rare success, maybe scoring a hit now and then. Suddenly, with only a few shots, enemy planes were falling from the sky. It felt as if some higher power was guiding each shell. Official Navy historian Samuel Eliot Morrison, observing in the Pacific Theater, would later note, "The sight of smoking fuselages and blazing debris across the water testified both to the accuracy of the anti-aircraft defenses and the remarkable effectiveness of the top-secret Mark 32 proximity fuse." The effect of this innovation spread rapidly throughout the Pacific Fleet. On August 12, 1942, before Helena even entered combat, USS Cleveland conducted a decisive trial that convinced naval authorities to commit fully to this technology. The test involved 3 radio-controlled drone aircraft designed to execute evasive maneuvers to challenge gunners. Although planned to last 2 days, the exercise concluded in under 2 hours. The first drone was destroyed on the second salvo of proximity-fused shells, the second fell on the fourth, and the third was obliterated by the very first burst. Observing Navy officials were astounded and immediately called off further trials, ordering full-scale production. Admiral William Spike Blandy, watching from Cleveland's bridge, remarked to his aide, "This changes everything. Every ship in the Pacific must be equipped with these rounds immediately." By the spring of 1943, proximity-fused ammunition was being shipped to the Pacific in unprecedented quantities. The initial 5,000 rounds were allocated to USS Enterprise, USS Saratoga, and USS Helena under the personal oversight of Commander W.S. Parsons, who would later oversee the arming of the atomic bomb aboard the Enola Gay. Security measures were extremely tight. The shells were stored in secure magazines guarded around the clock, and only gunnery officers were briefed on the true capabilities of the ammunition. To the crew, the rounds were described as advanced incendiary shells, accounting for their distinct markings. The operational impact became immediately evident. In 1943, despite proximity fuses representing only a quarter of all anti-aircraft rounds fired, they were responsible for over half of the Japanese aircraft downed by naval gunfire. The rounds per kill ratio plummeted from 58 for conventional time-fused shells to just 15 with the new technology, a threefold improvement that would grow as crews became more adept. Gunner's Mate Second Class Robert Chen of USS Essex chronicled the difference in his diary. In March 1943, he recalled, 300 rounds had been fired at attacking Betty bombers with no confirmed hits. By September, with the arrival of green-banded proximity rounds, 80 shots were sufficient to destroy 3 VALs. Chen wrote, "The crew thinks we've become better marksmen. They don't realize the shells are doing the targeting now." On June 19, 1944, in the Philippine Sea, Lieutenant James Van Allen stood on the flag bridge of USS Washington, monitoring radar screens brimming with incoming aircraft. Van Allen, known for developing shock-proof vacuum tubes, now witnessed their ultimate practical application. The Japanese had launched a massive carrier strike force of 423 planes, aiming to cripple the American fleet supporting the Mariana Islands invasion. The stakes were unprecedented, and the technological advantage of proximity-fused shells would prove decisive in the ensuing battle. In November 1942, Van Allen received his commission and subsequently devoted 16 months to instructing gunnery officers across the Pacific Fleet. He was acutely aware that every vessel was stocked with ammunition fitted with proximity fuses. While he understood the theoretical potential of this technology, he recognized that real combat often diverged sharply from calculated predictions. During the first raid, involving 2,069 aircraft heading in the direction 265 Angel, the Combat Information Center relayed the approach of the enemy. Admiral Mark Mitcher issued immediate orders. All fighters were to launch, and gunners were to man their stations. Hellcat aircraft surged into the Japanese formations, and those that penetrated the defensive perimeter encountered a ferocious barrage unlike anything previously recorded in naval warfare. From the bridge of USS Washington, Van Allen observed the sky erupt with black bursts, each marking a proximity-fused detonation. The impact on Japanese aircraft was devastating. A Mitsubishi Zero made a dive toward USS South Dakota, closing to within 1,000 yards of the ship. Van Allen witnessed the vessel's 5-inch guns engage with precision, firing measured volleys. The third round detonated merely 50 feet from the plane, tearing it apart. The fuselage fragmented, wings detached, the engine fell free, and the pilot tumbled uncontrollably. In correspondence with his wife, Van Allen would later describe the scene as systematic annihilation. Proximity fuses had transformed the fleet into near impenetrable fortresses. Despite their courage, Japanese pilots could not overcome this technological advantage. By the end of the day, Japanese losses included 315 carrier-based aircraft and 50 from land bases, while the U.S. sustained only 29 aircraft lost, primarily due to operational accidents rather than enemy fire. The lopsided nature of the engagement effectively neutralized Japan's carrier aviation capabilities. Conventional carrier strikes would never be mounted again. In desperation, Japan turned to an alternative tactic: the kamikaze. Aboard USS Bunker Hill, aviation radioman Charles Calhoun documented the aftermath. "We watched them falling everywhere, on fire, in pieces, sometimes intact, but all dead. Gunners were simultaneously laughing and crying. After enduring Japanese air attacks for 2 years, we were finally able to strike back. Proximity fuses made our guns virtually omnipotent." On October 25, 1944, at 0740 hours near Leyte Gulf in the Philippines, Lieutenant Commander Robert Roberts witnessed a new horror. A Zero, already aflame from anti-aircraft fire, deliberately crashed into the flight deck of USS St. Lo. The resulting explosion triggered torpedoes stored in the hangar deck, causing the ship to capsize and sink within minutes. This was the first major U.S. warship lost to a kamikaze strike. The Japanese had discovered a grim solution to proximity fuses. By sacrificing the pilot, the plane's momentum could carry it into the target even after being struck prematurely by detonation. Analysis of attack data confirmed the tactical shift. Between October 1944 and January 1945, conventional Japanese air assaults achieved a mere 2% success rate, registering only 23 hits from 1,092 attempts. Kamikaze operations, however, reached a 34% success rate, with 121 hits from 352 attacks. While the proximity fuse rendered standard assaults nearly suicidal, it still played a critical defensive role against kamikazes. During the Philippines campaign, American anti-aircraft guns successfully destroyed or deflected 231 of 364 kamikaze attempts, a 64% effectiveness rate, with proximity fuses accounting for 44% of 5-inch gun kills. Gunner's mate William Fomby aboard USS Nashville described the grim reality. "The Japanese attacked with disregard for survival. Even when our proximity fuses shredded aircraft into fragments, those pieces still struck at high speed. The fuses prevented far more damage than they failed to stop, yet any plane that penetrated the defense posed a deadly threat." By May 11, 1945, at 1500 hours, radar picket stations 60 miles north of Okinawa recorded a massive incoming force. Commander Baron J. Melanie of USS Hadley monitored the radar as Kikasui No. 6 approached, consisting of more than 150 coordinated kamikaze aircraft. Alongside USS Evans, Hadley formed the fleet's frontline early warning and first defense position. The Combat Information Center reported multiple raids converging from various directions, confirming the enormous scale of the impending assault. Proximity fuses had reshaped naval warfare, turning conventional gunnery into an exceptionally lethal force, while simultaneously prompting new, desperate countermeasures from a determined adversary. The technology's influence extended beyond statistics. It dictated the very nature of naval engagements in the final year of the Pacific War. Lieutenant Commander Melanie had trained his crew with unrelenting rigor, leaving no room for error. Each sailor knew precisely what his responsibilities were. The 5-inch gun magazines were filled exclusively with shells equipped with proximity fuses. The gun crews drilled relentlessly until they could sustain a firing rate of 15 rounds per minute per gun, the maximum rate that could be maintained over time without mechanical failure. At 15:20 hours, the first Japanese assault arrived. 12 aircraft approached from the north. Hadley's gunners opened fire at a range of 12,000 yards. Within moments, the proximity-fused shells detonated above and around the attackers. One plane fell at 8,000 yards, another at 6,000, and a third at 4,000 yards. A fourth kamikaze, already engulfed in flames, crashed just 50 yards off the ship's starboard side, showering debris across the deck, but inflicting no critical damage. This initial encounter was only a prelude. For the next hour and a half, the destroyer faced unrelenting waves of enemy aircraft. Gun barrels glowed red from continuous fire, and exhausted ammunition handlers were replaced on the spot. The proximity fuses functioned without fail, providing a deadly, almost rhythmic defensive pattern. Gunner's Mate 2nd Class Robert Eiley, stationed at Mount 52, recalled the intensity. The explosions occurred in rapid succession: fire, 3 seconds, detonation, and debris raining down. The cycle repeated with relentless precision. By 1615, however, Hadley's fortunes changed. 3 heavily damaged kamikazes, despite taking severe hits from proximity fuses, crashed into the vessel in rapid succession. A 4th aircraft released its bomb into the aft engine room, causing catastrophic damage. The ship suffered 30 fatalities, 68 wounded, flooding in engineering spaces and raging fires. Yet the crew's resilience held. Even as damage control teams fought to contain the chaos, the forward guns continued engaging enemy planes. When the action concluded at 16:55, Hadley had downed 23 enemy aircraft, setting a record for the most kills by a single destroyer in a single engagement. Commander Milani emphasized in his after-action report that the proximity fuse had been crucial. Without it, the ship would likely have been destroyed within the first 20 minutes. Even while damaged, the fuses allowed the gunners to maintain an effective defense when traditional shells would have been far less effective. The broader Okinawa campaign statistics highlighted the scale of the threat. Approximately 1,900 Japanese aircraft participated in kamikaze attacks. 368 U.S. ships were damaged, 34 were sunk, and U.S. casualties included 4,497 killed and 4,824 wounded. Post-war analysis indicated that without proximity fuses, U.S. losses could have exceeded 15,000 personnel, with over 100 ships destroyed. The introduction of this technology decisively shaped the outcome of the campaign. Meanwhile, across the Atlantic, a new threat emerged over London on June 13, 1944. At 400 hours, the chilling buzz of a V-1 flying bomb pierced the early morning air. The first missile of the main German offensive struck Grove Road, Bethnal, killing 6 civilians, including Mrs. Carrie Harrison, the first Londoner to fall victim to Hitler's vengeance weapon. Unlike the mass bombings of 1940–41, however, London now had a defensive system far more advanced than the public realized. On June 12, one day prior to the V-1 onslaught and 6 days after D-Day, Winston Churchill had made a critical strategic decision. Overruling security officials' concerns about the technology falling into enemy hands, he authorized the deployment of proximity-fused shells in the city's air defenses. Under General Sir Frederick Pyle, 500 heavy anti-aircraft guns, British 3.7-inch and American 90mm pieces, were arranged in a protective belt south of London. These weapons were integrated with SCR-584 microwave radar and M9 gun directors, forming a sophisticated semi-automated defensive network. The first week of V-1 attacks demonstrated the system's initial limitations. Anti-aircraft crews plotted dozens of incoming missiles, but most penetrated the defenses. Gunners fired continuously, yet success rates were dishearteningly low at just 24%. Squadron Leader Prudence Hill, monitoring operations at RAF Stanmore, described the early struggle. Plotting boards showed near-constant activity, but the majority of V-1s reached their targets. By the second week, a dramatic change occurred. Proximity-fused shells, flown directly from American production lines, reached the batteries. Suddenly, gunners began intercepting missiles much farther from the city. Success rates jumped to 46% in the second week, 67% in the third, and 79% in the fourth. The impact was so pronounced that German intelligence reported to Hitler that the British must have developed a previously unknown counterweapon. Gunner Sergeant Kenneth Brown, assigned to the 184th U.S. Anti-Aircraft Artillery Battalion near Biggin Hill, recounted the remarkable transformation. The arrival of proximity-fused ammunition converted the previously faltering defense into a highly effective, near-automated protective shield, saving thousands of lives and preventing massive destruction in London. Before the advent of proximity fuses, anti-aircraft crews faced a nearly impossible challenge. Shooting down a V-1 buzz bomb required pinpoint accuracy in both time and angle. Even the slightest deviation meant failure. A single second's miscalculation or a fraction of a degree off, and the projectile would miss its target entirely. Proximity fuses transformed this reality. Instead of relying on perfect aim, the shells themselves would detonate when they approached the missile, dramatically increasing the odds of destruction. The effect was akin to switching from blindfolded dart throws to hitting the bullseye with eyes wide open. On August 28, 1944, this technological breakthrough proved decisive. Early warning radar picked up 104 V-1s heading toward London. Anti-aircraft batteries equipped with proximity fuses intercepted 96 of them. RAF fighter aircraft managed to shoot down 4 more. Only 4 bombs penetrated the city's defenses. This event effectively neutralized the V-1 threat over London. Over a span of 80 days, a total of 9,300 V-1s were launched against the city, and proximity fuses accounted for the destruction of roughly 2,340 missiles. Without this defense, experts estimated an additional toll of over 20,000 fatalities and 50,000 injuries. Winston Churchill later recognized the significance, stating that the proximity fuse, more than any other single innovation, spared London from ruin at the hands of flying bombs. By December 15, 1944, attention had shifted to Antwerp, Belgium, a critical logistics hub for the Allied advance into Germany. Captain William Hartmann of the 407th Anti-Aircraft Gun Battalion reviewed the latest reports with satisfaction. In the previous 24 hours, his unit had successfully destroyed 89 out of 92 V-1s aimed at the city's port, a 97% interception rate, nearly unimaginable just weeks prior. Antwerp's 26 miles of docks handled about 25,000 tons of essential supplies daily, including food, ammunition, fuel, and medical provisions. Its continued operation was vital to sustaining the Allied front. Hitler was acutely aware of its strategic importance. Between October 24, 1944 and March 27, 1945, Germany launched 4,900 V-1s at Antwerp, over half the number fired at London. Initially, Antwerp's defenses struggled. Conventional time-fused shells were only partially effective, intercepting roughly 40% of incoming V-1s. Daily bombardments, sometimes reaching 30 bombs, threatened to disrupt the port's operations. The turning point arrived in mid-December when a Lancaster bomber made an emergency landing at Antwerp Airport, delivering 10,000 proximity fuses from Cincinnati on Churchill's direct orders. Technical Sergeant Joseph Crack, operating an SCR-584 radar unit, observed the immediate impact. Where previous targeting efforts often resulted in shells exploding harmlessly near the V-1s, proximity fuses ensured that nearly every burst destroyed its target. The system had essentially turned standard anti-aircraft guns into guided weapons. German operators launching V-1s from Holland could not comprehend the sudden shift in fortunes. Sites that had consistently achieved 80% success in striking Antwerp now saw 90% of their missiles destroyed mid-flight. Adjusting launch times, rates, and altitudes proved futile. The proximity fuse's mechanical precision rendered all German countermeasures ineffective. Sustained operations placed enormous demands on Allied crews. Private First Class Raymond Miller of the 126th AAA Battalion recalled the relentless pace. Ammunition trucks would arrive from the port and deliver new shells directly to gun positions, bypassing storage or paperwork. The order was simple: load and fire without pause. In one single day, a single gun position could expend 1,400 proximity-fused rounds, each representing a remarkable feat of engineering consumed in a matter of hours. By February 1945, the impact of the proximity fuses extended beyond the battlefield. German V-1 crews began to experience severe morale problems. Colonel Max Whittel, overseeing the V-1 offensive, reported to Hitler that continued bombardments of Antwerp were producing no tangible results, effectively throwing missiles into a wasteful furnace. Nevertheless, Hitler insisted that attacks continue, draining resources while achieving nothing. The proximity fuse had turned the tide of the air war over Antwerp, neutralizing the threat and ensuring that the city remained a lifeline for the Allied advance into Germany. By the end of the V-1 campaign, the air defenses protecting Antwerp had achieved results that bordered on the unprecedented. Out of 2,394 flying bombs that entered the defensive envelope, 2,183 were successfully intercepted and destroyed, an effectiveness rate exceeding 91%. Despite Germany's determined efforts, the port remained operational. Cargo ships continued unloading uninterrupted, fuel and ammunition kept moving forward, and the Allied advance into Germany never lost momentum. That logistical lifeline owed its survival to one quiet technological breakthrough: the proximity fuse. December 16, 1944, is remembered as the opening day of Germany's final large-scale offensive in the West, the Battle of the Bulge. Less commonly remembered is that it also marked the first time proximity fuses were used in ground combat. Just before dawn, at approximately 5:30 a.m., Colonel Oscar Alfred Axelson, commanding the 406th Artillery Group near the Belgian village of Monschau, began receiving urgent and alarming messages from forward observers. German troops were advancing in massive numbers. The thin American line, held by the 38th Cavalry Squadron, was facing an enemy force estimated at 10 times its size. Axelson understood the gravity of the situation immediately. Inside his ammunition depots were thousands of newly delivered artillery shells equipped with proximity fuses. These rounds had arrived only days earlier, accompanied by explicit and uncompromising instructions. Under no circumstances were they to be used against ground targets. The fear was clear: if such technology fell into enemy hands, the consequences could be catastrophic. Yet the alternative was grim. Without decisive intervention, the cavalry unit would likely be annihilated before sunrise. At 6 a.m., Axelson made a decision that would permanently alter modern warfare. He ordered his batteries to prepare the forbidden ammunition. The fuses were set for airburst detonation. Moments later, the first shells exploded above advancing German infantry crossing open, snow-covered terrain near Hofen. Unlike conventional artillery rounds that detonated on impact, allowing soldiers in foxholes to survive, the proximity-fused shells burst in mid-air at precisely calculated heights. The effect was devastating beyond precedent. Steel fragments cascaded downward in wide, lethal patterns, penetrating trenches, slipping behind walls, and tearing through areas previously considered safe. Vehicles offered no shelter. Trees provided no refuge. There was no effective defense against explosions that came from above. Lieutenant Richard Ralston, serving as a forward observer, watched the carnage unfold through his binoculars. His radio report was brief and clinical. The initial volley had burst directly over a German infantry company advancing in the open. Casualties were estimated at roughly 80%. Survivors were retreating in panic toward the nearby forest. Ralston immediately requested a follow-up strike on the tree line. The second barrage detonated among the branches. Shell fragments combined with exploding wood splinters, turning the forest itself into a weapon. The blast effects penetrated more than 100 yards into the trees, transforming what should have been cover into a killing zone. For German troops, many of them hardened veterans who had survived years of combat in Russia, France, and Italy, this was something entirely new: artillery that rendered all forms of cover useless. One survivor, Feldwebel Otto Hartmann of the 12th Volksgrenadier Division, was captured 2 days later. During interrogation, he described the barrage as unlike anything he had encountered throughout the war. Diving into foxholes offered no safety, as explosions occurred overhead. Fleeing into the forest only made matters worse, with shells detonating among the treetops. According to Hartmann, entire platoons were wiped out in seconds, and men shouted in terror that the Americans possessed a mysterious new weapon. News of Axelson's actions traveled quickly through Allied command channels. Within 3 days, Supreme Commander Dwight D. Eisenhower formally requested authorization to deploy proximity-fused artillery across the entire front. Approval was granted on December 21st. Almost immediately, American artillery units throughout the Ardennes began firing proximity-fused shells. The impact was dramatic and decisive. General George S. Patton, never known for restraint, wrote directly to the War Department on December 28th. He described the new ammunition, the shell with the peculiar fuse, as he called it, as extraordinarily destructive. In one engagement, a German battalion attempting to cross the Sauer River had been caught in a perfectly timed artillery strike using proximity fuses. Patton reported an actual count of 702 enemy dead. Those who survived were so psychologically shattered that they surrendered without resistance. Patton concluded with a prophetic observation: once every army possessed this technology, warfare itself would have to be reinvented. He added, with characteristic bluntness, that he was grateful the Americans had developed it first. The device reshaping battlefields from Western Europe to the Pacific had not emerged from glamorous laboratories or vast research campuses. Its origins were far more modest. Across the United States, production took place in converted bakeries, repurposed automobile repair shops, and even former Christmas light factories. Transforming Merle Tuve's experimental design into a weapon suitable for mass deployment was one of the most extraordinary industrial feats of the war. By late 1942, the scale of the challenge became clear. Each proximity fuse consisted of approximately 130 individual components, many of which had never been manufactured in large quantities before. Miniature vacuum tubes required tolerances measured in thousandths of an inch. Perfection was mandatory. A single flawed part could result in a malfunctioning shell, potentially killing friendly troops instead of the enemy. The industrial effort began in earnest at the Crosley Corporation in Cincinnati. Its owner, Powell Crosley Jr., who had built his empire producing radios and household appliances, converted his entire operation to fuse manufacturing. By January 1943, assembly lines were running continuously, day and night. One of the workers, Betty Morrison, later recalled her experience in a 1995 interview. Like most employees, she had no idea what she was truly building. Security measures were extreme. Workers were searched upon entering and leaving the facility. Personal belongings were prohibited. For 8 hours a day, Morrison and her colleagues sat at benches, carefully soldering microscopic components onto circuit boards. Supervisors told them only that they were assembling radio equipment for aircraft. It was not until after the war ended that Morrison learned the truth, that her hands had helped build the proximity fuses that saved countless Allied lives and reshaped the course of modern warfare. And the production numbers only continued to rise, reaching levels that even the engineers involved had once believed impossible. By December 1942, the production of proximity fuses in the United States had begun modestly, with only around 500 units being manufactured daily. Within 6 months, by June 1943, output had surged to 8,000 per day, and by December of that year, production had climbed to 40,000 daily. By the spring of 1944, American factories were rolling out an astonishing 70,000 proximity fuses every single day, a quantity that surpassed Germany's entire monthly output of conventional fuses. Among the factories, Sylvania Electric Products, located in Ipswich Mills, Massachusetts, emerged as the largest single producer. The facility, which had been farmland less than 2 years prior, employed 10,000 workers, with women comprising roughly 80% of the workforce. At the peak of production, they manufactured 100 million miniature vacuum tubes, achieving a daily rate of 400,000, two-thirds of the United States' total vacuum tube production before the war. The human toll of this industrial effort did not become apparent until decades later. Workers handled beryllium in the soldering process without knowing its lethality. In 2003, Pat Vlahos recounted that her mother, who had spent 3 years working at Sylvania, was diagnosed with malignant mesothelioma in 1983. She had no knowledge of the secret project she was contributing to. The exposure to beryllium ultimately claimed her life 40 years later. The scale of production reflects the extraordinary capacity of American industry. At the peak, 87 companies operating 110 factories employed 80,000 workers. Facilities ranged from university laboratories to factories that had previously made Christmas lights, from hearing aid workshops to automotive parts plants. Collectively, they transformed the nation's industrial base to produce the world's first smart weapon. Mass production also drove down costs dramatically. The first fuses in 1942 cost $732 each, roughly $11,514 in 2020 dollars. By 1945, the unit cost had fallen to $18, about $256 in 2020, achieving a 97.5% reduction while maintaining roughly 80% operational reliability, a manufacturing achievement unique to American industry. Security for the proximity fuse program rivaled that of the Manhattan Project, a necessity given the potential consequences if Axis powers had acquired the technology. To protect its secrets, the device was intentionally misnamed as the Variable Time Fuse by Captain S.R. Shoemaker of the Naval Bureau of Ordnance. Factories obscured the true purpose of the work, telling employees they were producing generic radio components or electronic parts for aircraft. Even the abbreviation VT was highly classified. When asked, gun crews were simply told it stood for variable time. At the Johns Hopkins Applied Physics Laboratory, security procedures were extreme. Every employee underwent FBI background checks, and the facility operated under such secrecy that neighbors noted groups of women arriving under the cover of night and departing in the morning, prompting curiosity about the building's function. Security personnel addressed everyone as doctor, regardless of actual rank, to prevent identification of key staff. Despite these measures, close calls occurred. In July 1943, a Dud proximity fuse shell fired from a destroyer landed on a Sicilian beach. A specialized recovery team was dispatched by air to retrieve the device before German forces could discover it. While the mission succeeded, new regulations were immediately imposed, limiting proximity fuse use over land until the Battle of the Bulge. A more serious incident arose in December 1944 when advancing German forces overran an American ammunition depot in the Ardennes, capturing 20,000 proximity fuses. Had German engineers recognized the fuse's potential, they could have developed countermeasures or replicated the technology. Remarkably, they examined the devices and dismissed their functionality as impossible. Post-war interrogation of Dr. Hans Gerschen, a leading German fuse expert, revealed their mindset. They believed no vacuum tube could survive the extreme forces generated during firing, assuming the Americans were engaged in propaganda about superweapons. Both Germany and Japan attempted to develop proximity fuses during the war, but never achieved operational deployment. German research was widespread but fragmented across multiple branches. The Luftwaffe explored acoustic fuses, the Wehrmacht tested photoelectric designs, Rheinmetall-Borsig experimented with electrostatic fuses, and the Navy pursued magnetic influence devices. Between 1940 and 1945, German institutions investigated between 30 and 50 different fuse concepts. Dr. Werner Rambowski, a leading German fuse expert post-war, explained that while German scientists understood the underlying theory and had even shared early prototypes with the British via the Oslo Report of 1939, they lacked three essential elements: miniaturized vacuum tubes that could withstand extreme acceleration, industrial capacity for mass production of complex electronics, and centralized coordination of research. The dispersed efforts proved fatal. By contrast, the U.S. concentrated all proximity fuse research under Section T at Mervis direction, avoiding fragmentation. Japan faced an even greater challenge. Lieutenant Commander Yuzuru Fukao of the Imperial Japanese Naval Technical Research Institute later admitted that by 1943, American anti-aircraft accuracy suggested some unknown technology, likely a proximity fuse, but its mechanism remained a mystery. Japan developed a photoelectric fuse by 1945 and conducted a single test, but lacked the industrial scale to mass produce it. Consequently, Japanese responses were tactical rather than technological, exemplified by kamikaze attacks which accepted near-certain loss of life to reach targets, a stark acknowledgement of technological inferiority. Beyond the impressive statistics and battle outcomes, the development of the proximity fuse was shaped by the personal dedication of individuals like Maro Tuve, who navigated immense technical and logistical challenges. Their work exemplified not only the ingenuity, but also the human cost behind one of the most significant technological breakthroughs of World War II. Merle's life was profoundly shaped by early tragedy. At 17, he lost his father to the influenza pandemic of 1918, leaving his family in financial distress. His mother took on laundry work to cover his schooling. The laboratory where he later worked bore the motto, "Save time, not money," a principle he internalized deeply. In wartime, hesitation could cost lives. After particularly grueling experiments, it was not unusual for colleagues to find him in his office at 3 in the morning, poring over casualty statistics from the Pacific Theater, calculating how much swifter production could spare human lives. James Van Allen experienced a similarly transformative journey from academic physicist to naval officer. After designing shock-resistant vacuum tubes, he insisted on serving aboard a naval warship to observe their performance firsthand. While on the USS Washington during the Battle of the Philippine Sea, he witnessed his innovations shielding sailors from harm. Later, he reflected, "The most rewarding moment of my scientific career was seeing theoretical physics translate directly into lives saved." For many wartime workers, the significance of their contributions only became clear decades later. Betty Thompson, who assembled components at the Crossley Corporation, recounted at a 1985 reunion that she had spent years unknowingly producing parts for proximity fuses. "I thought I was just building radio components for 40 years, she said. "When we were shown a film of the fuses in action, I started crying. Every tiny piece I soldered had been saving our boys from kamikaze attacks. We had no idea we were creating miracles." Lieutenant Robert Cochrane, who launched the first proximity-fused munitions from the USS Helena, carried the weight of his role throughout his life. In a 1975 interview, he described the experience. "The briefing made clear that this was a special weapon, but when I saw a Japanese plane disintegrate mid-air without a direct hit, I realized we had developed something transformative. It felt like witnessing the invention of gunpowder firsthand." Women in the applied physics laboratory, such as Technical Sergeant Marie Collins, were integral to ensuring the reliability of these weapons. Collins participated in quality control, testing fuses by firing them from specialized air guns. A near-fatal incident in which a fuse detonated prematurely underscored the stakes. The electronics they were producing were not merely technical components, they were lethal instruments, and any failure could result in American casualties. The impact of proximity fuses was evident from both Allied and German perspectives. Hauptmann Klaus Rieche, who observed their initial use in ground combat at Monschau and survived the war as a prisoner, later taught at Germany's reformed General Staff College. He explained to his students that the Americans had developed a weapon capable of rendering centuries of conventional military doctrine obsolete almost instantly. The statistical evidence reinforces the significance of these devices. In naval combat prior to the adoption of proximity fuses in 1942, it took between 500 and 2,000 rounds to destroy a single enemy aircraft, depending on conditions. After implementation, from 1943 to 1945, this number dropped dramatically to 155 rounds per aircraft, a 6 to 12-fold increase in efficiency. Across the Pacific War, proximity fuses accounted for the destruction of approximately 4,000 Japanese planes. Without them, conventional ammunition would likely have destroyed only 650, meaning that 3,350 additional aircraft eliminated by proximity fuses prevented an estimated 8,000 American sailor deaths and the sinking of 40 to 50 ships. The defensive use of proximity fuses against V-1 rockets was similarly decisive. In London, 2,340 V-1s were destroyed due to proximity-fused shells. Without these munitions, only about 560 would have been intercepted based on early week success rates, allowing an estimated 9,000 civilian deaths and 25,000 injuries. Antwerp's defense was even remarkable. Out of 2,394 V-1s engaged, 2,183 were destroyed, a success rate of 91.2%. If conventional shells had been used, achieving only a 40% interception rate, 1,400 more rockets would have struck the port, likely halting Allied operations in Northwest Europe. Proximity-fused artillery also played a major role in ground combat. During the Battle of the Bulge, around 200,000 shells equipped with these fuses were fired over 2 weeks. Their use is estimated to have caused 10,000 to 15,000 German casualties, highlighting once again the transformative power of advanced technology on the battlefield. Conventional artillery, using the same amount of ammunition, would likely have caused only around 2,000 casualties. The psychological effect of proximity-fused shells, which compelled entire units to surrender rather than endure airburst bombardments, is harder to measure, but undoubtedly played a crucial role in undermining the German offensive. The production numbers alone testify to the overwhelming industrial capacity of the United States. Over 22 million proximity fuses were produced, involving 87 companies, 110 factories, and a workforce that peaked at 80,000 employees, supported by an investment of approximately $1 billion, equivalent to about $15 billion in today's money. Analyzing cost per enemy aircraft destroyed reveals the remarkable efficiency of this technology. By 1945, the average proximity-fused round cost $18. Conventional anti-aircraft rounds, in contrast, required around 500 shells per aircraft, each costing $2, totaling $1,000 per target. Proximity-fused rounds achieved the same result with only 155 rounds at $18 each, amounting to $2,790 per aircraft. While the per-kill expense was higher, these shells dramatically reduced ammunition consumption by 69%, lowering wear on gun barrels, easing crew fatigue, minimizing supply demands, and greatly improving defensive effectiveness. The significance of the proximity fuse was acknowledged at the highest levels of Allied command, with multiple leaders ranking it among the most decisive technological breakthroughs of the war. Vannevar Bush, who directed the Office of Scientific Research and Development, provided one of the most comprehensive evaluations. He emphasized that proximity fuses increased the effectiveness of 5-inch anti-aircraft guns in the Pacific by a factor of 7. They became a vital component of radar-guided anti-aircraft batteries that ultimately neutralized German V-1 attacks on London and began reshaping land combat strategies, starting with the Battle of the Bulge. Aside from radar and the atomic bomb, no other innovation had a comparable influence on the war's outcome. General Dwight Eisenhower's judgment carried considerable authority, given his strategic vantage point. He noted that if Germany had successfully developed and deployed these weapons 6 months earlier, the Allied invasion of Europe would have faced extreme difficulty, perhaps insurmountable obstacles. The proximity fuse provided a decisive edge at a pivotal moment in the conflict. In 1945, Secretary of the Navy James Forrestal told Congress that the device had facilitated the fleet's westward advance toward Japan, preventing potentially massive losses in both personnel and ships. Admiral Willis Lee, commanding the battleships in the Pacific, spoke candidly. The proximity fuse made the fleet survivable against kamikaze attacks, without which half the vessels at Okinawa would likely have been lost. General George Patton praised the fuse for its tactical and strategic impact, crediting it with the success at the Battle of the Bulge and foreseeing the rise of intelligent weapons capable of autonomous action. Winston Churchill reflected on the fuse in his memoirs, noting that it protected London from flying bombs and, aside from the atomic bomb, was perhaps the most crucial weapon of defense during the war. He emphasized that American expertise in mass-producing complex systems provided the Allies with a critical protective advantage. Even post-war German assessments acknowledged the transformative effect of the fuse. Field Marshal Gerd von Rundstedt stated that traditional defensive positions became untenable in the face of proximity-fused artillery. Entrenchments and fortifications could no longer guarantee protection. The weapon represented a revolution in artillery that Germany could neither replicate nor counter. However, the fuse's production carried hidden human costs that surfaced only decades later. Workers in factories such as Sylvania and Crossley, handling beryllium copper alloys daily, were unaware of the material's extreme toxicity. Exposure led to chronic beryllium disease, which has a latency period ranging from 20 to 60 years, ultimately affecting hundreds, possibly thousands of wartime production employees long after the conflict ended. In 2001, Margaret Chen appeared before Congress to share the story of her mother, who had been employed at Sylvania's Ipswich mills. For 3 years, her mother assembled components for proximity fuses, contributing to the war effort with great pride. Decades later, the cost of this work became tragically clear. In 1978, she was diagnosed with beryllium disease, a condition she would ultimately succumb to in 1983 as her lungs filled and collapsed. A casualty of World War II, though delayed by 40 years. During the 1990s, the Department of Energy launched a medical screening program targeting former war-era workers, and the results were grim. Hundreds of individuals who had worked with electronic components during the Second World War were found to be suffering from illnesses linked to beryllium exposure. Many had already passed away, unaware that their contributions to the war had exacted a lethal toll. Dr. Robert Meyer, who conducted extensive research on beryllium-related illnesses among wartime employees, reflected on the situation. These workers, mostly women, had served the war effort directly, handling hazardous materials without protective measures because the dangers were not yet understood. Their efforts saved countless lives, yet many paid the ultimate price decades later. The proximity fuse itself was a technological breakthrough that reshaped military strategy. Prior to its introduction, artillery had largely been a direct-fire tool for over 5 centuries since the advent of gunpowder. Soldiers relied on trenches and fortifications for protection. The proximity fuse transformed this paradigm. Shells detonated above the ground, raining shrapnel into any cover below and rendering traditional entrenchments highly vulnerable. In his post-war analysis, Major General James Gavin, commander of the 82nd Airborne Division, emphasized the revolutionary impact of the fuse on infantry tactics. Entire retraining programs were required. Soldiers had to adopt dispersion and mobility over static defense, while overhead protection became essential for survival. Naval operations underwent similarly profound changes. Before proximity fuses, fleet movements relied heavily on dense fighter cover to ward off enemy air attacks. Afterward, individual surface ships could operate more independently, relying on their own anti-aircraft capabilities. This newfound flexibility accelerated campaigns such as island hopping in the Pacific. Admiral Raymond Spruance highlighted how the proximity fuse enabled strategic freedom, allowing ships to separate and maneuver confidently, knowing they could defend themselves. The cumulative effect was a multiplication of effective military strength through dispersed operations. The doctrine of air defense also evolved sharply. Before the proximity fuse, anti-aircraft strategy largely depended on saturating the skies with shells, hoping for accidental hits. The fuse's introduction allowed precision targeting, turning gun crews into skilled marksmen who could strike with calculated accuracy rather than rely on volume alone. Beyond its tactical significance, the proximity fuse marked a landmark in international scientific collaboration. The British originated the concept and conducted early research, while American industrial might provided the production capacity necessary for mass deployment. This successful model of Anglo-American cooperation became a defining feature of Allied efforts during the war and continued to shape partnerships into the Cold War era. During World War II, the development and deployment of proximity fuses represented a technological leap that neither Britain nor the United States could have achieved independently in time to influence the conflict's outcome. Sir Henry Tizard, reflecting on the collaboration, remarked that Britain had shared critical scientific concepts with the Americans, who in turn produced millions of operational munitions, a transaction he considered the most advantageous trade Britain ever executed. The success of the proximity fuse program laid the groundwork for post-war collaboration, shaping patterns of military and scientific cooperation that persisted into the Cold War. This initiative became a model for NATO's approach to joint technology sharing, intelligence exchange, and collaborative weapons development. The influence of proximity fuses extended far beyond the battlefield, seeding innovations that resonated in both military and civilian spheres for decades. Miniaturization techniques pioneered for the fuses directly informed the development of transistors and the design of integrated circuits. Similarly, James Van Allen adapted the shock-resistant methods honed during proximity fuse production for instruments aboard Explorer-1, the United States' first satellite, which led to the discovery of the Van Allen radiation belts. The organizational framework established during the program, universities conducting research in partnership with industry under government oversight, set a precedent for Cold War-era scientific research. The Johns Hopkins Applied Physics Laboratory, created specifically to advance the proximity fuse, evolved into a leading U.S. defense research center, contributing to innovations ranging from submarine-launched ballistic missiles to planetary exploration. Proximity fuse production also revolutionized quality control and industrial standards. The requirement for fuses to operate reliably under extreme conditions with a success rate of approximately 80% established benchmarks that influenced aerospace and defense manufacturing. Statistical process control techniques developed by Western Electric for the mass production of fuses were eventually adopted across American industry. Conceptually, the proximity fuse represented the first smart weapon, a munition capable of autonomous decision-making. Today, the legacy of this innovation is evident in radar-guided missiles, laser-guided bombs, and GPS-enabled munitions. The initial step toward autonomous weaponry can be traced to Merle Tuve's pioneering work with vacuum tube electronics. In May 1945, as American technical intelligence teams advanced into a defeated Germany, they uncovered extensive German research on proximity fuses hidden in underground labs and abandoned facilities. The findings were remarkable. German programs were widespread, encompassing virtually every major research institution. Their scientists had a thorough understanding of proximity fuse principles and had even produced functional designs. However, they lacked the industrial infrastructure necessary to convert experimental prototypes into mass-produced weapons. Reports from Colonel Howard Dix's team at the Luftwaffe research facility in Falkenroa confirmed the scale and sophistication of German work. Acoustic fuses had been tested at the Peenemünde V2 rocket center, photoelectric fuses evaluated at the Rechlin test range, and magnetic influence fuses developed at the naval facility in Kiel. Despite this technical knowledge, the Germans were hampered by technological limitations, particularly in vacuum tube production, and by an urgent shortage of time to implement their designs before the war's end. Albert Speer, Hitler's armaments minister, later noted that although captured American shells in late 1944 had revealed the existence of working fuses, German scientists initially dismissed them as impossible, doubting any electronics could survive the rigors of combat. The German inability to field proximity fuses underscored the true accomplishment of the Allies' program. It was not merely a triumph of engineering, but a demonstration of how effectively science and industrial capacity could be integrated under wartime conditions, a feat achievable at scale only in the United States of the 1940s. In contrast, Japanese attempts to comprehend or replicate the technology proved entirely unsuccessful. Post-war interrogations revealed that Japanese forces were left astounded by the effectiveness of American anti-aircraft fire, having no understanding of the mechanisms that had caused such devastation. Admiral Soemu Toyota, who led the Imperial Japanese Navy's combined fleet, later reflected on the turning point in aerial warfare during 1944. He recalled that American anti-aircraft defenses had reached an almost uncanny precision. Pilots reported observing shells that appeared to pursue their planes, detonating at precisely the moment needed to cause maximum damage. The Japanese initially believed this effectiveness resulted from an advanced form of radar guidance, never suspecting that the explosive shells themselves contained radar-triggered fuses. Captain Mitsuo Fuchida, famous for orchestrating the attack on Pearl Harbor, survived numerous missions under these new defenses. He recounted his experiences during strikes against U.S. aircraft carriers, describing scenes where even veteran pilots and their planes were obliterated mid-air by shells that seemed to explode independently of direct impact. The Japanese forces were left without any explanation. Some pilots speculated that the Americans had invented a death ray. This technological gap forced Japan to adopt kamikaze tactics. Lacking the capability to counter American innovations, Japanese strategy turned pilots into living missiles, embracing certain mortality in an effort to inflict any meaningful damage. While both Germany and Japan struggled to produce functional proximity fuses, the Soviet Union achieved success through espionage. In 1944, Julius Rosenberg, employed at Emerson Radio and Phonograph Corporation, illicitly obtained a complete proximity fuse and transmitted it to Soviet intelligence. The theft remained undiscovered until Rosenberg's arrest 6 years later in 1950. By that time, Soviet forces had already begun producing their own proximity fuses, directly modeled on American designs. During the Korean War, these Soviet versions were used effectively against U.S. aircraft, demonstrating how military technology can circle back against its originators. David Greenglass, Rosenberg's brother-in-law who testified against him, later noted that Julius regarded the stolen fuse as more immediately consequential than atomic bomb intelligence due to its deployable nature, and by many measures, he was correct. Historians frequently rank the proximity fuse among the 3 most transformative innovations of World War II, alongside radar and nuclear weapons. Unlike the atomic bomb, which was employed in only 2 attacks, proximity fuses were used continuously from January 1943 until the end of the war in August 1945, impacting thousands of military engagements. Dr. Arnold Kramer, a military historian at Texas A&M University, observed that the proximity fuse had perhaps the most measurable effect on both enemy casualties and Allied survivability of any clandestine weapon. Estimates suggest that approximately 25,000 enemy aircraft were destroyed or damaged, over 5,000 V-1 flying bombs neutralized, and tens of thousands of enemy soldiers killed by proximity-fused artillery. Allied lives spared likely numbered in the hundreds of thousands. Beyond raw statistics, the proximity fuse reshaped modern warfare. It ushered in the era of precision munitions, proving that technological edge could decisively influence combat outcomes. The weapon demonstrated that democratic nations, leveraging the combined power of civilian scientific expertise and industrial capacity, could outpace even the most determined totalitarian regimes. Every proximity fuse carried the imprint of human ingenuity, sacrifice, and relentless problem-solving. In essence, it exemplified the profound interplay of science and strategy on the battlefield, leaving a legacy that extended far beyond the immediate conflicts of World War II. Merle Tuve never fully recovered from the emotional toll of wartime research. In 1946, colleagues discovered him sitting alone in his vacant Johns Hopkins laboratory, tears streaming down his face. All those young men who perished while we were still perfecting the fuse. If only we had worked even a few weeks faster, how many might have survived?
For the remainder of his career, Tuve turned toward astronomy, seeking distance from the instruments of war. In contrast, James Van Allen channeled his wartime experience into groundbreaking space science. The hardening techniques he pioneered for proximity fuses later protected delicate instruments aboard early satellites. When asked about his military research, Van Allen would modestly remark, "I helped save lives. Everything else I did pales in comparison." The women who manufactured these fuses, Betty Morrison at Crossley, Marie Collins at Johns Hopkins, and thousands of others whose identities are now forgotten, performed their work quietly and meticulously. Many never learned the full purpose of their labor until decades later, if ever. Their deft hands and careful attention to detail directly contributed to saving innumerable lives far from the production lines. The servicemen who used the fuses recognized their value instantly. Gunner's mate Anthony Pui of the USS Helena captured the sentiment of many. Those green-banded shells felt like divine protection. Each round loaded promised that an American pilot or sailor somewhere would survive because of it. The development of the proximity fuse represented a massive undertaking, roughly $1 billion in 1940s currency, equivalent to $15 billion today. It mobilized 87 companies, 110 factories, and 80,000 workers, consuming resources that could have otherwise produced thousands of tanks or hundreds of ships. Yet its worth is evident in what never occurred: battles avoided, vessels preserved, cities spared, and lives saved. Every Japanese aircraft intercepted before reaching its target meant fewer casualties among American forces. Every V-1 rocket destroyed before striking London saved civilian lives. Every German soldier eliminated by airburst artillery could no longer threaten Allied troops. Admiral Chester Nimitz perhaps summarized its strategic significance best. The proximity fuse was equivalent to 10 infantry divisions, 100 aircraft squadrons, or an entire naval fleet. It amplified military power through innovation, exemplifying the uniquely American approach to warfare. History often glorifies generals and admirals, dramatic campaigns, and heroic maneuvers, while neglecting the scientists, engineers, and laborers whose ingenuity made victory possible. Merle Tuve passed away in 1982, his essential role largely unknown outside scientific circles. James Van Allen became a household name for his contributions to space research, while the impact of his wartime work faded into the background. Figures such as Lloyd Berkner, Richard Roberts, and Henry Porter are noted primarily in technical accounts. The countless women who assembled proximity fuses remain largely invisible to history. No statues commemorate their efforts, no medals were awarded, yet their precision and courage, often handling dangerous materials without fully understanding them, saved more lives than most decorated soldiers. Perhaps their anonymity reflects the very nature of the proximity fuse program. Its success relied on collaboration. British scientists exchanging knowledge, American researchers solving seemingly impossible problems, factory workers producing devices with unwavering skill, and military personnel deploying these innovations effectively. There was no single hero, rather a collective effort of hundreds of thousands committed to a shared mission. 2 weeks after the first devastating deployment at Monschau, as 1944 gave way to 1945, German officer Klaus Richter recorded his final diary entry. The Battle of the Bulge was faltering, with German forces forced into retreat. American artillery equipped with proximity fuses continued its relentless bombardment, each airburst lighting up snow-covered battlefields with lethal precision. "We are not only facing American soldiers," Richter wrote, "but American science itself. Their munitions anticipate, calculate, and determine the exact moment to strike. We are confronting the future, and the future is prevailing. God help Germany, for we have awakened a giant whose weapons are guided by intellect." Richter could not have anticipated the full extent of his insight. The invention of the proximity fuse represented more than a technological breakthrough. It reflected the unique strength of open societies harnessing civilian intellect for wartime purposes. While German scientists often worked in isolation and Japanese researchers were cut off from critical information, teams of American, British, and Canadian experts shared their discoveries freely, tackling technical challenges collaboratively. The proximity fuse was, in essence, a product of democracy, conceived by innovative minds, produced by skilled workers, and deployed by soldiers defending freedom itself. Its creation depended not solely on scientific expertise, but on mutual confidence, trust among allies exchanging classified information, between academic institutions and government, and across the civilian-military divide. Such cooperation was virtually impossible under authoritarian regimes, giving democratic nations a crucial advantage. From its initial concept in October 1939 by Wasbutment to large-scale production by 1943, the proximity fuse journeyed from British urgency through American ingenuity to the Allied victory. Along this path, it directly saved countless lives, shortened the war's duration, and inaugurated the era of intelligent munitions that persists today. The proximity fuse demonstrated that victory in war could stem not only from valor and perseverance, but also from technological superiority and industrial capacity. It proved that weapons equipped with thought could amplify human effectiveness far beyond prior limits. Above all, it illustrated that nations willing to pool knowledge and resources could accomplish feats unattainable by totalitarian states. Within the delicate vacuum tubes engineered under the guidance of James Van Allen, enduring forces once considered destructive, and the intricate circuits designed by Lloyd Berkner to detect the approach of enemy shells, lay the difference between triumph and failure. Countless women, often unrecognized, soldered components with extraordinary precision, shaping the outcome of battles, the defense of freedom, and the very course of history. The proximity fuse became the most strategically significant covert weapon of the conflict, not because of raw destructive power, but because it was deployed broadly, reliably, and at decisive moments. It was a thinking weapon, and in enabling thoughtful application, it preserved the freedom of those who wielded it. German troops at Elsenborn Ridge, trapped in bunkers that offered little protection, faced more than just overwhelming firepower. They encountered the future. A future in which the integration of intelligence into weaponry magnified human capability beyond previous imagination. This future, conceived during the desperate months of 1940, refined under the trials of global war, and validated across battlefields from the Pacific Islands to the European continent, originated from a deceptively simple question:
what if an artillery shell could act intelligently? The solution to this question helped secure the survival of free nations and fundamentally reshaped modern warfare.